So, update on the calendar and where we are now. It's actually on the backboard for you guys to see that part 1, the 4.1b long answer part of the test, is going to be on Monday. The second half of Monday is going to be a work day on the test review, with the test review being due on Tuesday. You also have your forever card quiz on Tuesday as well, which I think yesterday I posted it in Google Classroom was cards 28 through 38, something like that, 29 through 38, something along those lines. I'm going to go ahead and freeze the screen and pull up those forever cards so we can make sure that the numbers are matching what you guys have in your notes. And also to show you something weird about the ordering, because I actually have the order a little bit different online than I do in our notes, and there's a purpose for it. There's a reason for it. But that forever quiz is going to be on Tuesday first thing, and the second half of Tuesday is going to be us going over test review questions because it will have been due in Google Classroom that morning. And then we have that practice test that's going to be due on Wednesday. That's the bonus practice test, but once again, we know that practice multiple choice are a really good thing to do, right? And that'll just be like normal. Now, this is our first test of the semester, so as you guys know, tests are the majority of your grade. You do have your large forever quiz from right after break. I believe your MenWeb is probably not up to date because I fell pretty behind as far as with the algebra class and then getting sick. So this weekend I should be able to get all that updated. That way you guys can see what your grade is before this first test. But to be honest, it really will determine your grade. In many ways, just because it's the first big test. So you will have that forever quiz, that's a 10-pointer. You will have the one from after break, which was the 15-pointer. So it's not going to be the only thing in that category. That bonus practice test, remember, is worth 3 bonus points. So there will be a few other things in there, but it really will have a big impact, at least for right now, until we get another test in, which we're going to try to do before the end of the grading period. Kyle?
Isn't this also the same test that can get half points back?
Because we're at the new semester and so everything gets to start over again? Yes, so that is a little like a, okay, all right, after you finish the test, it's okay. But at the same time, I am trying to encourage you as we're starting off, right, our testing of this semester, to really dig in and really be ready. And that's another thing with Spiritual Office Week, etc., that the calendar has had to budge a little, but I think that's in our best interest as long as you use the time well. Okay, so 4.4 is the last homework. That's the one that's due tomorrow. 4.4 is the last homework before we start our review. So you guys should be able to start the review over the weekend. But we won't be grading officially going over it until Tuesday. I'm pulling up the forever cards really quickly just so that we can make sure everything looks good. I think we have that. If you guys are checking out with me to make sure everything looks good, I think card number 30 was 4.1a, all the integration rules, which would mean card number 29 was the definition of the antiderivative. That's where we started this chapter, was the definition of the antiderivative. Remember, the antiderivative is what is produced from an indefinite integral plus c. And the antiderivative is also the function whose derivative is the integrand, is little f. And then we went to, the basic integration rules being forever card number 30. And then I think, just want to make sure I'm getting it all okay. I think we wrote this height times base and height 1 plus height 2 times base. We might have rearranged those a little bit. I think otherwise we probably did that okay. Definition of the definite integral with partitions or with n approaching infinity. Was number 33 the one that we did yesterday, the fundamental theory of calculus? Yeah. Okay, so I think we're all right. What we didn't do yesterday is we didn't label the integration with absolute value as a forever card, but I do want to make it a forever card just because it's a procedure that is easily lost if we're not continually reminding ourselves of it. In that we see an absolute value, we're like, we'll ignore it till later, and we don't realize we have to split up the bounds. We have to split up the bounds if there are any zeros of the function in between, and then we can pull out those absolute values. We're going to peek at that example that we didn't get to finish yesterday really quickly before getting into the new notes that you guys were setting up. But then you just wrote down this one, right? Average value of a function. And what was the next yellow box that you guys should have just been writing down?
FTC part 2.
Okay, here's the weird thing. What's the next forever card?
FTC.
MPT for integration. And on the next page. Do you guys see any similarities? We haven't done this one yet. Do you see any similarities between this card and the card before? The one that you have in your notes. Okay, you have it in your notes. Do you see any similarities between the one that you have in your notes, average value of, and this card?
Yeah, the
See it?
is
You see it? Okay, didn't we just talk about how capital F is the antiderivative of little f, which means capital F prime is little f? Check it. If this is the average value of a rate function, and this is an instantaneous rate, isn't this really just old-fashioned MVT from before? Average equals instantaneous, just realizing that these are rates. So this is technically the last one that we're going to be writing down today, but I wrote it in our forever cards. I wrote it directly after average value, even though in our book the order is a little bit switched. Because average value, it's like, oh yeah, if that's average, sweet. MVT says average equals instantaneous, and remember, little f is like a rate equation. Little f is like a rate equation. So we could actually put this in terms of the antiderivative and see our MVT, our old-fashioned MVT. But anyway, we'll get to that one. And then I wanted just to show you, I'm not incorrect. We're ordering this weird, okay? So FTC part 2 is actually not going to be the next one. So we have number 35 being average value. Number 37 being FTC part 2. And then we're going to put number 36. The last forever card, remember I said we're going back to our motion packet? That'll probably be tomorrow that we go back to our motion packet. But wait a minute. Why is it a good thing that we're going back to motion tomorrow? Because you have the long answer motion one on Monday. So we're going to finish up 4-4, have that homework due tomorrow, get back into our motion packet tomorrow, remind ourselves of where we were in 4.1b, the types of long answers we were doing, etc. And then you'll be ready for that long answer on Monday. Sound good? Okay. So with that being the plan, let's go ahead and get back into our notes. Let me pause the video real quick so we can pray for today. You guys just heard me label average value of f of x as forever card number 35. Forever card number 35. So let's go and get that one labeled. This one's going to be forever number 37. I know it's weird, but it's true. Our MVT that's coming is going to be number 36. But what we didn't get to label yesterday was forever card number 30. Oh, we didn't have a yellow box around. Poor little guy. Forever number 34. Yeah? There we go. But I added a couple things, if you guys noticed, on the forever card online, forever number 34. First of all, how do we split up? We set y, or we set our integrand, we set our f of x equal to 0. We're solving for the zeros. And that's how we split up that integral. So what was an a to b, I guess I technically wrote that up above in the forever card online. What we start with is just a good old-fashioned integral from a to b of the absolute value of f of x dx. But sadly, the only way to deal with those absolute values is to pull them out after splitting up the definite integral into however many pieces we need, using however many x-intercepts we have, and then adding them all together. And this one down here, we had two different x-intercepts, so we had to split it up twice, right? And both of them were in between that range, or I should say that domain from -3 to 3. So we had to split it up at -1, and then we had to match it to get to 1, and then we had to match it to get to 3. And if you guys remember from that property of integrals, we can go from a to b using c's and d's and e's. We can split up however much we want. But what we didn't get to finish yesterday was actually solving this. In period 6 we did, and that was what I ended up reporting. So if anybody checked out the recording from yesterday, you would have seen the rest of this example. Because they didn't get to go over homework questions. We ended up doing notes first, and homework questions we'll do today for them. So you guys, in some ways we're behind, but in some ways we're a little bit ahead because we don't have to go over homework questions. But if you were absent yesterday, it might be that you should have been able to see the evens online, but you wouldn't have seen us go over anything. So feel free to stop by if you need to have us finish that up. But what are we missing in solving and finishing this problem? I have all of these little antiderivatives of b's minus a's. What have we not found yet?
You have to plug in the.
I haven't plugged in, or why haven't I plugged in? Like I showed that I needed to plug in. I was running out of time yesterday. Yeah, I need to find the antiderivative. So who is the antiderivative of x cubed minus 1? It is going to be an x cubed, but it's going to be an x cubed to x to the n plus 1 over n plus 1, right? And then minus, what's the integral of any constant? Just the variable. And can we also double check by bringing 3 down, the 3's cancel, x squared? And then what's the derivative of negative x? Negative 1. Now, who am I plugging into this guy? Yeah, negative 3 to negative 1. Absolute value. There we go. We're going to do the exact same thing for all the rest of them, in that we have the exact same antiderivative. Just from now, negative 1 to 1, and then we have the exact same thing, which is 1/3. Now, guys, what I'm about to do is super dangerous, but we're all working on this together. You guys are hopefully double-checking my work. And so we can catch any mistakes if they occur. What I'm about to do is FTC in my head, at least partially. Ready? Because I just don't have a lot of room. I'm going to write the absolute value over here, but here we go. So I'm going to do f of b, which is the antiderivative of negative 1. Ready? We have negative 1/3 minus the negative 1, so negative 1/3 plus 1, which is going to be 2/3. F of b minus f of a. I don't even think I need to put parentheses as long as I'm careful. Trying to simplify this as much as possible. So plugging in negative 1, and then plugging in negative 3. So that'd be negative 27 over 3 is negative 9. Negative 9 minus a negative 3. Negative 9 plus 3. So it'll end up being negative 6. So minus a negative 6. I'm going to go ahead and write that just so that you guys are double checking. You can make sure I'm good. So far, seemingly so good? Okay. So then moving on, we're going to plug in 1. That's going to be 1/3 minus 1 minus 3/3. That's going to be negative 2/3 minus, and then plugging in negative 1, and negative 1/3 minus a negative 1. Negative 1/3 plus 1 is negative, no, plus 1 is positive 2/3. Not cancel. Not cancel. If it cancels, I'm in trouble. If it cancels, that's a little bit confusing. It should have gone down through a 0 to have above and below to cancel. But I split it up in all the zeros. And then plugging in 3, that'd be 27 minus 3. Sorry, 27 over 3, which is 9 minus 3 is 6. And then minus, and I have 1 minus, sorry, 1/3 minus 1. So negative 2/3. Double checking that one because it got messy. 27 is 9 minus 3 is 6. And then 1/3 minus 3/3 is negative 2/3. Got it. Super dangerous once again, but you guys are all double checking. Good? Okay. So I'm going to end up with, that's going to be a plus. I'm going to do plus 18/3 because that makes life so much easier. That's going to be a negative. That's going to be a plus. And then I can make that 18/3. I think I end up with this being 20/3. And then plus 4/3. And then plus 20/3. Do you guys realize that I had to do this first before I took the absolute value? This was positive, stayed the same. This was negative. So after I added, I then flipped the sign. And then actually, technically, after I subtracted, I flipped the sign. And then still positive, I kept it the same. Long story short, please, 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 one of the most common mistakes on these guys is you see a minus and you're like, you mean plus, and that's wrong. Absolute value doesn't mean you change any subtractions to addition. It means that you take any final product and you make that a positive if it was a negative. But if there's subtraction, you must do that first. Absolute value doesn't cancel that out. So long story short, in context of the problem, there was a positive displacement, a negative displacement, and a positive displacement. Like yesterday, how I was talking about, if I started here, and if I moved to the left for, actually this one would be a little different. This one would be positive displacement first. I moved for a lot to the right, I moved for a little bit to the left, and then I moved a lot more to the right, pretending I could walk. If I had done the positive plus the negative plus the positive, I would not have gotten the total distance traveled. I would have gotten the displacement. My example yesterday with the earlier e to the x minus 1 was that movement to the left a little bit and then movement to the right a lot more. But if we did that positive with that negative, we would just get this little baby displacement. And that is not the total distance that I travel. I need to take the absolute value of each part of the journey, the absolute value of every single portion, and saying, I need that total magnitude. I need that total magnitude to add it all up. My final answer is 44. Now pause real quick. Does anybody in your group have a calculator? Can you guys make sure that your calculator understands absolute value? Because this is us having to do it by hand, not with a calculator. But guys, can you find the absolute value in your calculator? Do you remember where that is and where that was? Because if it's a calculator question, just throw it in. If they were to ask you for total distance traveled and it was a calculator question, you would take the velocity, the rate, you would throw it in absolute values and be like, you do it, Mr. Calculator. Let's make sure he knows how. How do you find the absolute go away value?
Alpha window.
You could do the shortcut, nicely done, alpha window. Otherwise, you could go to math and you could go scrolling. I think you have to go over to numbers and then there's the abs. But absolute value is something that's commonly used. So yeah, you could do alpha window. You could steal your integral, right, number 4. But then you could also, going from -3 to 3. But you can also do alpha window to grab that absolute value. And then, what was our function? X squared minus 1?
Yeah.
Does our calculator know how to do absolute value? And the answer is, let's see if we know how to do absolute value. Oh, I don't know if that's 44 thirds. You guys see that little, you can go to frac, right?
Yeah.
What does it not let me do it from here?
Alpha y equals.
Oh yeah, thanks, number 4. You can go fraction to decimal or decimal to fraction. It goes whichever way you want it to go based on what you're doing. No. Does that not work? Hard, Cooper. I thought it did.
You just do 44 divided by 3.
I know, I'm just kind of bummed it. Did you guys get complete with fraction?
That's cool.
Did any of you guys just go to 44 thirds?
Hold on, I'm still editing it.
Bummer. If you guys noticed, the calculator did not do as good a job as we did. Do you see it? The calculator is technically using approximation techniques in order to be able to solve this integral. They're kind of doing that Riemann sum thing that I was talking about before. Actually, I don't know if that's exactly how they're doing it. They could also be changing this function into a Taylor series, and then but that's CalcBC stuff. But anyway, all that to say, the calculator didn't do as good a job as we did in the sense of we found it exactly and it found it approximately. And you might be like, well, forget the calculator. I should never use it. Okay, you'll never say that. I know. But coming back. On the AP, is it going to mess you up? Look. How many decimal places on the AP?
3.
It's going to be accurate enough for the AP. I didn't mean to, like, that's weird. I actually do not remember this ever being such a bad approximation. You guys all got the same decimal, right? The weird, like, 7263? Yeah. That's confusing to me as to why it's so bad. But long story short, we'll be okay with how precise the calculator is and what the AP is expecting of us. It's just really weird it's that bad. I typed it in. Yep, I typed it in. 44 thirds is the best answer. I don't know. We'll keep going. But anyway, absolute value, we reminded ourselves of how to use it in the calculator because definitely sometimes you'll be able to if they ever say total distance traveled. I know I'm introducing the motion forever card early. It's coming. Total distance traveled. We throw in velocity and absolute value. We would need to split up the integral at every stopping point because for me to do motion to the right and then do motion to the left, what needs to happen in between? This velocity. I'm having a positive velocity and then a negative velocity. What had to happen? A change in sign at a 0 and then another change in sign at a 0. Right now, is it possible if I were to ever stop and then keep going?
Yeah.
But I'm still going to split up at the zeros just in case if I'm doing it by hand. So absolute value, whenever you split up at the zeros, maybe sometimes you don't need to, but maybe sometimes you do. And so we have to always split up at zeros. And the motion example of going to the right, going to the left, going to the right, and I need to add up all those distances, maybe that helps you at least a little bit internalize what's really going on with absolute values and why we need to split it up. But, staticky hair. I don't think that's mine, it's too short. Anyway, but displacement would say, just throw in velocity, I don't care. I want to see how displaced you end up, your final position minus your initial position. But anyway, all that's still coming in motion packet tomorrow. Let's get back to those forever cards. Those forever cards that we need to keep talking about. Out of the entire AP, the most confusing, I don't know about this. This page is the simplest, most confusing topic on the AP. Or maybe the most confusing, simplest topic. I don't know how I want to say that. However, there is one little thing on the AP that can be so easily confused by what you're supposed to do, and yet it's so easy if you're able to see. It's not that it's a complicated topic, it's just that it's a confusing one. Not complicated, just confusing. Where have you seen the word average before? Average rate of change. An average rate of change, if we're talking about average rate of some sort of function f, I know in your card, in your forever card, it's motion, so it's average position, or average velocity. So we use position, but if we're trying to, and I'm just going to add a different page, don't write it down. But if we were to talk about that old forever card, let's go forward here. We were doing average rate of change of position. I think technically we used S instead of X on that card. So it's S of T. And so technically that's the same thing as average velocity, right? And that was your S of B minus S of A all over B minus A. But then we realized, you know what, we could change this to be any F of X, average rate of F of X, which would be the average of the, it wouldn't necessarily be velocity, it would just be average rate. So you could almost say average F prime, that's kind of awkward though, so we'll just say average rate. And that could have been F of B minus F of A. We can find the average of anything, or the average rate of anything. This gets a little confusing, because this says we don't just look at average rates of functions that were given. The average rate of F of B minus F of A over B minus A, but this is always looking forward. So if it was S of B minus S of A over B minus A, you would be working with, what function is this again in motion? Position. You'd be looking at position and you'd be finding its average rate. You're looking forward to the derivative. You're not taking it, but you're approximating it, hence that average idea. This card says we get to deal with something, not looking forward, but looking at it. It's not average rate of, it's average value of. You're going to hear me when we're doing lots of AP practice. You're like, okay, the word average, what is it? Are we looking forward to its rate, or are we looking at it for its value? I know that's weird, but this one is looking forward to the rate. We're looking forward, just if anyone's watching the video, not in class today, we're looking forward with this formula. We're looking forward to the rate whenever we do a change in y over a change in x. But this one, average value, we're looking at what we've been given. So if I want to find the average value of f, I would need 1 over b minus a times the integral from a to b of f of x dx. Maybe as we keep going forward, I can kind of expound on that just a little bit, but for today and for what I want to accomplish today, let's go ahead and get some examples done. Just realize that this is a complicated topic in the sense of reading a question and knowing exactly what they want. But that idea of, are we looking forward, f of b minus f of a over b minus a, or are we looking at 1 over b minus a, the integral from a to b of f of x dx. So in this problem, when I give you, who's x of t? What is it probably talking about, x of t? the position and probably of some sort of like random particle on an x-axis if you really want to be honest, because it's talking about just the x's changing, or it could be anything moving horizontally. If they say find the average rate, okay, the average rate of x, they're saying look at x and look forward to rate. Okay, look at a position, look forward to like a velocity. That's what I would do, x of 5 minus x of 0 all over 5 minus 0. And I would plug in and I would solve. But what if they had given us the velocity function instead? I'm going to use this same function just so we can match it up. It would be negative 4t plus 3. What if they had given us velocity and they said find the average of velocity, and we already have him. We're looking at what we already have. We want the average of what we already have. That's when we would use 1 over 5 minus 0 times the integral a to b, just kidding, 0 to 5, of our negative 4t plus 3. And the crazy thing is, guys, if you look at this one up here, we would be plugging in 5 to the position function and plugging in 0, subtracting and then dividing by. I can make this 1 over 5 times x of 5 minus x of 0. And I would plug it in. But question down here, wouldn't I be needing to solve this integral? Wouldn't I be needing to anti-derive? So wouldn't I be going to negative 4t squared over 2, aka negative 2t squared plus 3 times t? And wouldn't I be evaluating that from 0 to 5? And then wouldn't I be multiplying that by 1/5? Oh, do you see the exact same thing? This one says go plug in 5 to this function. No, but this has a minus 1. Yeah, but he's going to have a minus 1, and minus a minus 1, the plus c, the constant, is not going to matter. It's going to end up being x of 5 minus x of 0 all over 5 minus 0. They are the exact same thing. Both of them are finding average velocity in this motion example. Both of them are finding average velocity or average rate. One just says, hey, I can look forward to a rate, and one says, oh, I already have a rate, I'm looking at it. But they're doing the exact same math. Just one is looking forward with the slope, and one is looking backwards with an integral. Yeah.
Did you mean for the velocity order negative 2t plus 3t? Or
oh, I didn't do squared. Thank you. Thank you. Thank you. Okay, FTC part 2, what's going on there? Believe me, we'll come back to this. Average rate versus average value, just looking forwards or looking at. We'll come back as we see more AP problems, etc. But FTC part 2. FTC part 2, you guys have already written down. If what's inside an integral is continuous on an open interval, which means the antiderivative is both continuous and differentiable, then for every x in the interval, the derivative of the antiderivative. Wait a minute, the derivative of the derivative of it, they're inverses. Because they're inverses, they undo each other. What's weird is if you have a u, you're going to end up having an f of u times u prime. I'm going to go ahead and zoom in on this one real quick so that we can go ahead and do the next example. Because to be honest, what I need you to be able to do is actually use the theorem and maybe not totally understand the theorem right now. Let's see if we can use the theorem. So, if I'm taking the derivative right now of an f of t dt, I could technically, the idea of it, and I'm going to do it pretty fast, the idea of it, I could take with notation, even though I don't know the actual function itself, I could put with notation, capital F is his antiderivative of t. I would evaluate that from a to x, which means I would go ahead and plug in the b, f of b, plug in the top bound, minus, plug in the bottom bound. But guys, check it. If I did know what the antiderivative was, if I was able to do that math, when I take the derivative, isn't the derivative of any constant just going to be 0? So this little f of a guy, he's just going to be a 0. So to be honest, that little bottom dude, whether he's a 2 or a 4 or a negative 10 or a 173. Whatever he is, when I plug him in, he's a constant, and his derivative will be 0. The bottom bound, as long as it's a constant, doesn't matter. He's always going to go away. And then the top bound, well, I'm going to take the derivative of the antiderivative, but why did I do all that work? Don't I just end up right back at the beginning? I end up right back at the beginning, and I could have gotten there just by plugging in the x and saying, oh, okay. The derivative of an integral from a to x of f of t dt will always just be f of x. So instead of doing all this extra work, we say, okay, forget that. And to be honest, sometimes this antiderivative might be impossible, or at least beyond your pay grade. I mean, beyond where you are right now. So we're just going to go straight to the answer. That's what the card says. But this one down here, if you're curious as to why this is a little different and has a use problem, I shouldn't do that without a bad voice, is because if I go plugging in an x squared to the antiderivative, okay, that f of a, the antiderivative of a, still won't matter because his derivative is 0. But when I go to take his derivative, isn't that going to be a chain? And aren't I going to have to do a... It doesn't work when I do it. Thank you. Aren't you going to have to do one of those?
Yes.
And then, okay, well, wait. But hold on. This guy is still little f. Okay, that's good. So it's almost like I can plug in the u and be done, but it's not quite enough. I also need the, one more time, Kyle. Thank you. I also need that guy as well. So I can almost skip all of this and not even think about it and just plug it in, except I also need the u. And that's why the FTC part 2 is what it is. So when I come over here to the next page, I'm going to zoom out just so you guys can still see this in case you're still writing. If I was to do something like this function, and they define for me, I don't know, they call whatever, is the definite integral from pi over 4 to x. They could call him whatever letter they want. Now, some of you might be a little bit confused because you're like, wait, I see an x there. Be careful. The x and the x are there and there. If they were to tell me f of 2, I'd have to plug in 2, or f of 10, I'd have to plug in 10. Not to here. Those are t's. X's go with x's. But this one just says, hey, find f prime. I'm like, okay, sure. I mean, I guess so. Whatever. F prime is just the derivative of f. And who's the derivative of f? Well, I would take the derivative of the other side. At pi over 4, does he make a difference? No, he's just a constant. And if I did know how to anti-derive, which you guys don't yet know how to do a u sub for integration, but if you did, you would end up plugging in the x and plugging in the pi over 4 and then taking the derivative, and then guess what? You would end up right back where you started, just with a dun 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 dun. Wait, really? Yes.
Okay, so like I understand that FTC, like part 1, like the antiderivative and like integration will get you the area underneath. What does this do?
This allows us to be talking about a function in terms of what we call an accumulator that, to be honest, we just haven't really seen much of yet. And accumulators are very helpful in the sense of they're saying from some starting point of a rate, let's talk about all the different x's. So it's like, hey, if we're moving, it's able to be talking about the accumulation itself over time instead of at one instant over all the instants. If that makes sense. And then being able to take a derivative of is able to say, like, hey, is the accumulator increasing or decreasing? It's helping us kind of be able to work with it and do that derivative work even though it's defined by an integral. If that kind of makes sense. But this guy, this whole like a to x or a to u, they're called accumulator functions. And we just haven't been able to work with them much because, let's be honest, we just learned what a definite integral is and how to do it. So guys, if we're looking at these couple examples, I'm going to do them just kind of fast, just how to use FTC, because I just want to write down or get down this card for you guys so that you guys can use the formulas in order to try to finish up that homework tonight. Because in this forever card, let me just go steal it real fast. It really is old MVT, and so the problems are going to feel a lot like old MVT, like find a guaranteed x equals c, etc. I'll get a better copy of it later, but for right now, this works.
Whoa.
I know. It's going to feel a lot like old MVT. So you're just kind of given directions that say, find the special X, find the special C, find the special such that this is true. You're just going to be plugging into a different derivative, or a different formula, I should say, instead of this old-fashioned formula. We're not working with the antiderivative, we're working with the rate or the little f, so we're going to have to use the average value equation to get the instantaneous equal to the average. This is forever card number 36. So the only forever now that we're missing is the motion one that we'll be talking in our motion packet tomorrow after we grade homework. But I was just going to show you real quick for this guy, since it's an A to U, you would be able to solve it by just using your f of u times u prime. So it'd be f of whatever is inside, plugging in the u to the variable spot. Oops, the u is just x squared. And then we just need to do separately, after plugging in the u, our u prime, and that's good. This one, it's so great, plug in, except, oh wait, exactly. I would actually need to flip the bounds first, hold my properties, and then I would be allowed to, in taking a derivative, just plug in. Now, this is just an x, so you can also think about it as a u, but its u prime is just 1, so it doesn't make a big difference. But that's FTC Part 2 applied. If you guys want to check out a couple more examples if you're doing homework, you do have those ones that you could check out in the video or in the notes. But MVT for integration. Once again, feels a lot like old MVT. Check it, see, we're done. We just didn't get this example. Feels a lot like old MVT. You're just solving for special C's. So what I'm going to do right now, guys, after Algebra 1, so we're just going to let that class just happen, if that's okay.